Okay, guys, this is the simulation of example number 1 of uncontrolled rectifiers, lecture 14. So if you want to see the questions, how to do the simulation, so go and see this problem. So if I brief the problem, we have a sine wave power supply, which is amplitude, the peak value is 100 volts. So that is this amplitude, which is the peak value, it is 100. And the frequency is 50 hertz, and there's a phase angle is 0 because it started from here. So we have this sine wave, and so it is asked to use a appropriate diode model. So I have used 1N4007, which is this diode, which has these properties. Breakdown voltage is 1000 volts. So this is, since this is 100 volts power supply, so it is more than enough. And so it can drive up to 1 amp of, it is not shown here. Forward current is 1 amp, right? So driving 100 ohm resistor with the 100 watt peak value, which is probably the peak value is 1 amp, so will be enough. And this is the capacitor that I'm going to use. I will put it as in the question. So it is asked to use a capacitor with the value of 1000 microfarad. So I will simulate without the capacitor first. So I have added current ammeter, which is showing the DC voltage, and this is actually this is showing instantaneous voltage, and this is the voltage across the diode with respect to this point. And this is a source current. Source voltage can be displayed itself. This is load current, and this is the output voltage. So it is all good to go. So I can go to analysis, transient. And so this is a 50 hertz signal. I know the periodic time is 20 milliseconds. So I am going to simulate it for 3 cycles. So which is 60 milliseconds will be enough. I'm going to start from 0 initial condition, which means like the capacitor doesn't have any voltage, and everything is started from 0. So this is how it looks like. I go to and use separate curve options, so I can see now. You can see this is my supply voltage, which has a 100 volt of peak and 50 hertz, and the load current. The output voltage is this one, right? During the positive half cycle, G1 conducts, and during the negative half cycle, the D1 stops, and the current of the output will be 0. And the diode current, the diode voltage VG, during this period, it is approximately 0, and during the negative half cycle, the negative half cycle appearing directly across the diode. The source current, you can see source current during the positive half cycle only as the load current, and then during the negative half cycles, source doesn't provide any current because this diode is open circuit now. So all these things can be visualized from here. So what I'm going to show you how to get this average and RMS voltage from this waveform, right? So let's take a look at the average and RMS voltage of the output voltage. So you need to just click on this waveform, right? Just click on this VL, which is the output voltage. Then, so you have selected this waveform. Go to process, get the averages, right? So average, so it will do this averaging from 0 to 59.96, almost 60 period. So they will take this period, total period, and get the integral and get the average. So average value is 31.36, which is the DC voltage of this output, right? Which we have used from our equation. So when you found from calculated value, so you can compare with this value from the simulation. And the RMS value also for 49.43. So you can do by manual calculations and compare with your simulated values. This is the average value, and this is the RMS value of your output voltage. So that can be used for any other waveforms as well. Okay. And the other thing is how to get this harmonics and total harmonic distortion of the output voltage. Similarly, select the waveform, go to process and Fourier series. And you can start the sampling frequency from any time. So here I have just, like when it's starting, like there is some kind of transient happening, but I'm assuming like 20 milliseconds of time, it has reached to steady state. So I'm going to do my Fourier analysis from 20 milliseconds from here. And the stops it here, right, 60 hertz by default. And the base frequency, I know like this waveform has a 50 hertz of base frequency. That is my fundamental. You can have more samples, but 4096 will be enough. A number of harmonics to be displayed, 16 will be enough for this case. And the format would be this cosine would be okay, d into cosine as a cosine waveform. And so you have selected the harmonics to be received from the output voltage VL. So then press the calculate. You can see the 0 is the DC offset, which is the average DC value, which was the same one that we found from the previous case, like 31.33. It is the DC voltage. 0 is the DC voltage. And the first harmonic, the fundamental component is 49.3. And the second harmonic is 21.14, which is 100 hertz. This is 0 hertz, and this is 50 hertz, and this is 100 hertz. This is like multiplication of 50 hertz base frequency. 0, 50, 100, 150. And the phase angle, don't worry about that, like we are not interested about phase angle. These are the amplitude of each harmonic. And the total harmonic distortion is 43.941%. Okay. So if you are not familiar with the total harmonic distortions, go and see the definition for total harmonic distortions in the inverter lectures, single phase inverters. I have discussed what is the total harmonic distortion. So it is already can be found from the simulation pretty much easily using this way, right? And also you can display that harmonic spectrum when you click the draw. So you can see now this DC component is DC rectified DC voltage 30 point something, and this is a fundamental component 50 something, and the second harmonic, third is almost 0, and fourth likewise is decay. And this is the phase angles. So pretty much easy to get those things like I explained. Now take a look at what will happen to the output voltage when you put the capacitor. So I will connect the capacitor to here, and I will simulate analysis transient. Now you can see the output has now, the ripple has already gone. Now it has a very small ripple. So if you want to calculate the peak-to-peak ripple, what you can do is just zoom it out for a bit. And this, put it here, put it to the peak, and put it to the valley here. Yeah, so this is the peak-to-peak ripple around like 15.93, which is around like 16 volt of peak-to-peak ripple. And out of 100, like 60%, around 60% of peak-to-peak ripple. And you can see now this the diode current. So this is peak-to-peak ripple. Now you know how to get that. See how what happens to the diode current. Like initially the diode carries around like 29.96 of amps of current at the startup to charge the capacitor, and the diode only conducts for very small regions, right? As the capacitor has a charge, and when the capacitor does not has the charge, so it only conducts to a small region to get the capacitor charged to its peak. Okay, so diode's voltage waveform is not like the what you have seen in the previous case, like not like this one. Okay, so the diode voltage waveform has changed because diode is only conducting when it is the capacitor does not have the charge, and it draws like a very large current, like around 15 amps pulsative current. But at the start, it draws like around 29.96. So if this diode cannot accept this kind of like a peak surge current, like if this peak surge current of the diode is less than 30, so definitely the diode will fail because this is undesirable for the diode to carry that kind of large current. So I have asked like whether the diode can survive if the capacitance is increased. So we can just redo the simulation. I'm going to add the like 4.7 millifarad capacitor and do the simulation again. Now you can see the diode current is almost starting current surge is around like 138.98, and then later it is reduced to 22.4 like that. Okay, but if this is higher than the peak current of the diode, definitely the diode will fail. So we can just go and look at the diode datasheet and see how it goes. And the diode output, the peak voltage appearing across the diode is around minus 200. And sometimes it reaches to 1.3 and again reaches to 100 minus 200 volts. Okay, so that is basically lower than this peak reverse voltage of the diode. So that is all about this simulation. So now you know how to get the harmonics and everything. Even now you can really look at the harmonics of this waveform. So output voltage. Now this you can see this. Now the DC components is almost zero, as almost 100, which means like your DC value is 100, and all the harmonics are disappeared, like after adding the capacitor. Okay. So that's all about the simulations. I can just show you how the data sheet. So this is 1 and 4007 series diode. So you can see this is a peak forward surge current from 4001 to 4007 for all diodes. It should be 30 amps, right? But when we add this 4.7 microfarad capacitor, surge current has reaches at the first cycle to around like a very large value, around 200 amps. So that is undesirable. The diode can fail. But for 1000 microfarad region, so it was safe. So if we go look at back. So now we can see this diode current is around like 138, which is the data sheet said it should be lower than 30 amps, so the diode will fail. Okay, so if you add the 4007 microfarad to get a flat DC line, you can't add your this diode. So either you have to use a diode with higher peak repetitive peak surge current rating, then you can use it without an issue. But if you use 1000 microfarad capacitor, now this surge current is almost 30, right? 30.7, which is acceptable, but there's a slight peak-to-peak ripple. But if you are satisfied with this ripple, you can just use this diode. And if you want to have like a flat DC line with higher capacitors, most probably you have to use a different diode model which can accept this kind of peak surge current. So these small things you have to be careful. That's why the transient simulation is important. Like this is what you see from the steady state, right? So the steady state current is like very surge current is now less than 20.83, but at the startup, there's a large current flow and potentially could destroy your diode. So that's why transient simulation is also important to see what's happening at the initial startup to steady state. Okay, I hope this video has explained you things regarding how to get this average voltages and how to get the Fourier series and how to get the total harmonic distortion. So this is all about this single phase rectifiers. I suggest you to develop and try this example number 2, which is for bridge rectifier application. You can add 4 diodes and see how it goes and try to get the answers. Okay, thank you for your time for this lecture is completed with this explanation. So that's it.